Hello guys, this is going to be chapter 7 review. It's not going to be too long hopefully. So let's get right into it. The first thing, so chapter 7, the main thing about chapter 7 is talking about the plasma membrane. So we already went in depth last video, but we'll go over it again. So this top part here is the plasma membrane. And we talked about how it has a hydrophilic head right here, which means it likes water, and hydrophobic tails, which face each other. So this creates a plasma membrane is a bilayered, bilayer, bilayer of phospholipids. So bilayer means two. So as you can see here, we have one phospholipid and a second phospholipid, and the hydrophobic tails are facing towards each other, so that the hydrophobic tails do not face the water because they don't like water, and the hydrophilic heads face the water. This allows for the creation of the plasma membrane. And when you have a hydrophilic head or a hydrophilic part and a hydrophobic part on the same molecule, it's called amphipathic. We talked about that before as well. Continue on to what a fluid mosaic model is. It's basically the accepted model of the cell membrane structure. Um, Basically, the whole point of it, while I was reading the book, is the fluid part is talking about the fluidity of the membrane, and the mosaic part is talking about the proteins inside of the membrane, which we'll talk more about later. Um, we also talked about the movement of phospholipids. We have the lateral movement. So the lateral movement would be the movement where the the first layer of the phospholipids, which is lateral, so from here to here and back, and it can also happen on this side, just this side. They'll swap right here. So this is called the lateral movement. It could also go that way. So these phospholipids move. Um, uh, these phospholipids move in a lateral movement, and this happens around 1 million times a second. So very, very fast. So your phospholipids are always moving um, laterally very fast. We have the flip-flop method, which means that one phospholipid on one layer would switch with one phospholipid on the other layer, but that happens very rarely. All you have to know is it happens very rarely, doesn't happen as much as lateral movement, and it just happens very rarely. So that is it about the movement of the phospholipid. We'll move over to the fluidity of the phospholipid. So one thing to know is that a phospholipid could be viscous, which means it has no movement, which is really bad. Um, when you have no movement, that means you need your membrane to be fluid. If it's viscous, it wouldn't work. Your membrane proteins wouldn't be able to go in there. It would just be stuck together, very tight. Um, we have a more fluid-like structure here. As you can see, we have unsaturated fats, which means it has double bonds and it creates kinks. So it has more or less hydrophobic interactions, which makes it more fluid. So it's a good thing to know what viscous and fluid means, but what actually maintains the fluidity and the viciousness of your plasma membrane is cholesterol. So this is cholesterol right here. All of these are cholesterol, and basically what it does, it uses temperature. At on moderate temperatures like normal temperature, it reduces fluidity, so it makes it more viscous. But at lower temperature, it makes it more fluid. So using temperature, it acts as a fluidity buffer. So what that means, it allows it to adjust to the temperature to change the fluidity accordingly of the plasma membrane. So you can consider it a fluidity buffer. Um, so now we need to talk about, now that we're done talking about the actual plasma membrane, the movement of the phospholipids, and the fluidity of the membrane, we can talk about some protein structures in the membrane, plasma membrane. We have two types of proteins: an integral protein, um, an integral protein which is inside the cell and is usually amphipathic, meaning hydrophobic and hydrophilic, because as we can see, this part right here is exposed as a hydrophilic, or this whole area right here. And then this part right here, this inside, is inside a hydrophobic part. And then again, this part right here is hydrophilic. This part right here is hydrophilic. I did not type that properly. I don't know why it's not typing. Okay. So again, an integral protein is hydrophobic, usually hydrophobic and hydrophilic. It goes inside of the, it goes inside, it goes inside the plasma membrane, all the way through. So again, within the membrane, also amphipathic. Now, peripheral protein is just stuck to the plasma membrane. It's just outside of the plasma membrane, and that'd be connected outside the membrane, and they're probably usually hydrophilic because again, they're completely exposed to hydrophilic regions. Now that we talked about the type of proteins that can be in a plasma membrane, we need to talk about the functions of them. So, of course, they can transport. This would be facilitated diffusion and active transport. Enzymes, so helping breaking and forming of bonds. Signal transduction, which basically uses a receptor to connect to a protein, and the protein will then release a solute or something. Something will happen when when the receptor is full. Cell-to-cell recognition. This is the use of glycoproteins, and we'll talk about that more later. Intercellular joining, meaning the holding of cells. So again, that would be uh, the joining of cells. So proteins would connect to each other to hold the cells together. And attachment to the cytoskeleton and ECM. So this would be the cytoskeleton would mean the proteins are attached to um, filaments, microfilaments, microtubules, and intermediate filaments out inside the cell. And then the ECM, or the extracellular matrix, which we'll talk about later, the proteins connect to it outside the cell. Now we're talking about cell-to-cell recognition. Real quick, um, this green part right here is going to be your glycoproteins. And what it does is each cell has a different, or each type of cell has a different glycoprotein-like complex. So when this cell right here, cell 1, goes to this cell right here, oh sorry, goes to this cell and connects to the glycoprotein, or the glycoprotein, and the glycoprotein has a specific complex. It knows what cell 2 is. So this tells this other cells what cell is it. Is it um, this cell, or is it that cell? They have so many different types of cell in your body. It just identifies the cells, which is really important. That is it for that slide. selective permeability of a membrane specifically, we have to talk about nonpolar and polar molecules. Nonpolar molecules are basically molecules that have no charge. Um, this happens usually when the electronegativity of the uh, atoms are the same, and when they combine, they have no partial or negative charges. So these molecules can enter the cell easily. So nonpolar means not charged. Um, Polar molecules, however, that are charged, they need transfer proteins because they can't just go through the the membrane. So nonpolar uses simple diffusion, which we'll talk about later. It uses simple diffusion, meaning it can just go straight through the membrane. However, polar molecules need proteins to help them cross the membrane. So that is what selective permeability means. It selects what it what sorry. Selective permeability is the selectiveness of what goes in and out of the cell. So with this nonpolar and polar mechanism, it determines what can and cannot go in the cell easily or not easily using diffusion. As an example, H2O or water is polar. Special is polar. So sorry, is polar, which means it cannot cross the membrane easily. It has specialized proteins called aquaporins. The aquaporins are specialized transfer proteins or channel proteins that are used to transfer large amounts of water. And we'll talk more about transfer proteins later, but to know that aquaporins has the special name of a protein that transfers just water into the cell is really important to know. To the next slide. Okay, now we get to talk about diffusion. So diffusion is the random movement of particles from usually high to low. So what that means is when you have molecules move in random positions, and that's normal. However, when you have a higher concentration and a lower concentration, that creates a gradient, and naturally the higher concentration will go to the lower concentration. That's just how diffusion works. So for example here, we have these molecules, the yellow ones, and they're bouncing around in all different places, same as these ones. But as you can see, we have a lot more on this side right here. We have a lot more molecules on this side, and we have a lot less molecules on this side. So what would naturally happen is net diffusion creates a gradient from high, this is high, to low. So naturally what would happen over time what would happen is it will go onto this side. And this side basically means this side shows that the solute or the substance is equal on both sides. This just means net diffusion is zero. To say um, diffusion is still going on. Diffusion does not stop. It does not mean that these molecules are just going to stop moving around once it reaches zero. Um, these molecules are still going to be moving in, and molecules are still going to be moving out and through the membrane. Net diffusion is just zero. It means equilibrium. It means when one solute goes in, another solute will leave. and that will just continue happening. That's just equilibrium. So that is diffusion. Now let's talk about passive transport. So again, we need to talk about first simple diffusion. So we have these molecules right here that are non-polar. I'm gonna do um, non-polar. So if they're non-polar, all they have to do is just go right through the cell. They will go right through the cell. They'll go. You'll have the molecules on this side in no time because it is called simple diffusion. They are non-polar. They go right through the membrane. It's called simple diffusion. And they're moving from a concentration again of high concentration to a concentration of low concentration. So if I made this less, for example, and they don't need energy to do this. Passive transport is the transport with no energy. So what would happen is over time these solids will go into the cell, and that's because that the inside of the cell does not have this as much solid as outside the cell using passive transport. Another type is using facilitated diffusion. So these two right here, using proteins is called facilitated diffusion. Facilitated diffusion. And we have two types of facilitated diffusion. We have channel proteins and we have carrier proteins. So these are channel proteins. Because as you can see, we have this long channel right here. It's just a one big channel. So these are channel proteins. And what channel proteins do is basically polar 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 molecules like these. These are polar molecules right here. They can just seep through down and not have to worry about the hydrophobic interactions they're going with. So theoretically speaking, they could just go down this gradient and eventually end up here. Again, the concentration is high to low. That doesn't change for passive transport. So they'll go down this path right here, right here, and end up in the inside here using the channel proteins. Now we have another one called carrier proteins. I do not know how to spell carrier proteins. And what this is you have a big molecule, large. It could also it could also be polar, also be polar. So what would happen is the protein will open up, take a molecule, and eventually it will carry it like a boat. It will carry it to the other side to, of course, another low gradient with lower solute. So you have your high gradient here, and you have your low gradient here. So this is going to be your low, and this is going to be your high right here. All these. So that is facilitated diffusion. Again, we have simple diffusion, which is the use of no proteins, and it just goes right through the membrane. We have the use of channel proteins, which allow polar molecules to just seep right through like a bridge. And we have carrier proteins, which allow large and possibly polar molecules enter in the cell. Now we can talk about osmosis, and I already drew most of it over here. Osmosis is the specific diffusion of water. And we'll show that right here. As you can see, we have a little test tube here with a semi-permeable membrane, so something like a plasma membrane, semi-permeable membrane, that only allows water to enter, to go through it. Um, as you can see, we have more solutes on one side, so we have more solutes on this side than, so more solutes on this side than we do on this side. So what would happen? What would happen again if we kept our solutes high on this side and a little lower on this side? We still had our membrane. Our water level will change, and I'll explain why. Right here we can see our water is level with each other at the beginning. But water goes towards a higher concentration because it attracts more water because water has a hydration shell. And a hydration shell basically means it just goes around the solutes and that uses up a lot of water. So what would happen is the water level would drop here and the water level would rise here. So you'll have something that looks like this, where the water level is up here and the water level is down here on this side because the water is moving in this direction because it's going from a low concentration to a high concentration. These solutes use a lot of water or need a lot of water, while these solutes have is less in quantity, so it doesn't need as much water. So again, the water will rise on this side because it's collecting. It's collecting on this side. And again, this is due to the semi-permeable membrane where the water is going. And this is diffusion of water where water is going through the semi-permeable membrane. That is osmosis. Tonicity. This is all about tonicity. This whole slide is basically tonicity. Tonicity. And there is a couple different types of tonicity, and we'll be talking about a red blood cell and a plant cell, and the different types of tonicity. So the three types of tonicity is hypotonic, isotonic, and hypertonic. Now, I wrote here solution. On the book and on what you guys learned, they don't write solution, but I wrote here solution for a reason, and I'll explain why. Okay, so let's talk about what we're talking about here. So the solution, when you talk about solution, we're going to be talking about the outside of the cell. What is, I'm going to draw a circle here, what the outside of the cell is. So again, this solution outside the cell, on all of these cells. So we'll talk about what what a hypotonic solution is. A hypotonic solution means it has a less concentration than what we're going against with. So what this means is if our red blood cell is 1% concentration, this is the concentration, it's 1% concentration, then our solution would be less than that. So, for example, the solution might be 0.5% right here. 0.5%. Now, again, we have to know that water goes from a hypotonic solution or a hypotonic to a hypertonic. So looking at this right now, we can tell that this has a greater percentage than this. This makes the inside cell hypertonic because you're placing a cell in a hypotonic solution that makes the cell hypertonic. And remember, if you remember, water always goes towards hyper. So that means H2O is going inside the cell, causing this red blood cell to burst, and the name of this is called lyse or burst. Now, talking about it for a plant cell, it's the exact same thing. If you have a 1% solution here, this could be 0.5%. Water is going inside the cell. But since a since a plant cell has a cell wall, it does not burst. And this is going to be called turgid. This is going to be called turgid. And this is normal. This is normal for a plant cell. Now we talk about an isotonic solution. For example, isotonic means the exact same. So if this is a 1% solution inside this blood cell, then the solution would be, or yeah, the solution would be also 1%. But remember that this time water goes inside the cell and also outside the cell because net diffusion is zero and water will always diffuse. Diffusion is always occurring. Not just stop. So water will go in and out of the cell. Same thing for the plant cell. 1%, 1%. Water is going in and out. The name of this is just called normal. You can call this, for the red blood cell, you can call this normal, or you can call it biconcaved. As for plant cells, this is going to be called flaccid, and this is not normal. The normal one is going to be turgid for a plant cell. Now if we have a hypertonic solution and the red blood cell is still 1%, that means that the solution is more. So this could be 5%. And remember, water always goes from hypotonic to hypertonic. So the cell will lose water. The cell will lose water and go outside, meaning it loses water. Same thing for a plant cell. It loses water. The plant cell has a 1% solution, but the hypertonic solution, it has a 5%. What this is called in a red blood cell, you could either just say shriveled, or you can say crenated. As for a plant cell, we call this plasmolyzed. Molyzed. So, as we can see here, hypertonic solution means it has less of a solution than what's in it. An isotonic solution means it's both the same, and a hypertonic solution means whatever is outside of what we have is going to have a more of a concentration. And again, through diffusion, it goes from high to low with water. So water will go from a place of low concentration to a place of high concentration. And that is why water moves the way it does. That'll be it for tonicity. We'll talk about active transport now. So active transport uses an protein as well. It uses a active transport protein to move things from a concentration of low to high. So for example here, we have a sodium-potassium pump that is pumping sodium and potassium. And as we can see here, we have just say 2 potassium on this side. So we have a very low concentration of potassium on this side, and we have like 7 potassium on this side, which is a high concentration. So we can write here high, we can write here low. For only for potassium, only for potassium. But it's going to be low for sodium and high over here for sodium. But what this protein is doing is it's taking ATP right here. It's taking ATP and it's putting in two uh, it is putting in the cell 2 potassiums. So we're putting here we're putting in 2K plus. But we are going to be and that's going to be from a low concentration to a high concentration, if you remember, using active transport. And it's going to be taking 3 sodium from this side and moving it to this side. Again, from low concentration to high concentration. So what we're doing here as well, which we'll also talk about a little bit later, is we're creating an electrochemical gradient. This is because we're subtracting 2 on this side because these are ions. Sodium, we have uh, sodium and potassium, which are ions, and we're minusing 2 charge from here because remember, we're taking 2 2 potassiums which means we're minusing 2 on this side. But then we're going to be adding 3. We're going to be adding 3. This leaves us with a plus 1 charge. This creates a positive charge on this side and a negative charge on this side. This is where electrochemical gradients come into place. We have an electrochemical gradient, which just means you have a high to low gradient of ions, and this is what this is creating. You're gonna have less ions on this side, and you're gonna have more ions on this side. That is why this side is positive, and why this side is negative. Now, we need to talk about a few things here. Um, Membrane potential, all it is the voltage across a cell membrane. So the voltage across specifically this cell membrane, if we were to calculate it, that would be the membrane potential. An electrochemical gradient is just when you have a high to low of ions. So again, here we do have a high to low concentration. We have more sodium on the top, and we have less sodium and potassium on the bottom. This creates a positive and negative electrochemical gradient. And how these are created is through pumps, electrogenic pumps. A pump, so it's a specific pump that creates the electrochemical gradient. So any pump that creates this gradient, electrochemical gradient, that is an electrogenic pump. So for example, this sodium potassium pump right here is an electrogenic pump because it is creating a membrane potential and it is creating an electrochemical gradient. But we'll talk about another example of a electrogenic pump, and that would be a proton pump. So as you guys can see, it's using ATP in the proton pump. It's taking a hydrogen from low concentration and is shooting them on this side, creating a abnormally high amount of hydrogens on the outside of the plasma membrane, creating a positive charge on the outside, and it's taking all the hydrogens from the inside of the cell, so it's going to be minusing. So you're going to have a minus charge and a positive charge because you have a bunch of hydrogens on the outside and only like only like a few hydrogens on this side. So it creates a, so that is what the proton pump does. So again, a proton pump is a type of electrogenic pump that pumps hydrogens outside, of the membrane, creating an electrochemical gradient. Again, this is a gradient. You have a high amount of hydrogens and you have a low amount of hydrogens. So that's the chemical gradient. Now we need to go over something called a cotransporter. So it's just a type of secondary active transport that couples the downhill reaction. So here, the hydrogen ions are forced into a high concentration outside using ATP, the energy of ATP. But look, you have a high amount of sucrose here and a low amount of sucrose here. But we don't have ATP on the outside of the cell. So what do? We take the hydrogens that was pumped out and we use a co-transporter called the hydrogen sucrose. For this example, we have sucrose that wants to go from low to high, and it's called a hydrogen sucrose cotransporter, and it's using the hydrogens from the proton pump to go back in the cell and also bring in the sucrose with it. So it acts as a coupling for the downhill reaction. And this basically create this example, we could see it as a battery, for example. We could see it as like a battery where we're charging the battery with the proton pump, charging the battery with the proton pump, and then we're using the battery to bring things into the cell. So the cotransporter is just a type of secondary active transport that couples a downhill reaction, and that would be it for active transporter. Active transporter uses the ATP to bring stuff from low to high. That's all that means. And as for the last thing we'll talk about is exocytosis and endocytosis. So for exocytosis, it's pretty much easy. You're basically taking whatever is inside the cell and bringing it outside the cell. So this will come and you will have, so basically all of your, that is not the same color. I'll leave it. So whatever's inside the cell going outside will be called exocytosis. So whatever is exiting the cell is going to be exocytosis. So since this solute is going to go outside the cell, it's going to be called exocytosis. It's pretty much that easy. Now endocytosis is entering the cell, but we have three different types of endocytosis. For example, when we have food entering the cell, a large food molecule will be engulfed by the plasma membrane. So this is part of the plasma membrane, and it engulfs this food particle. Now it takes it inside the cell. Now we have a food vacuole. This is called a food vacuole. Engulfed the food. So now the food is inside the food, inside a vacuole, so it's called a food vacuole. And this process is called phagocytosis, when food is entering the cell. When fluids, for example, water and stuff, like liquid, wants to enter the cell, it it's called pinocytosis, cell drinking. The same thing happens, but this time it's coated in proteins, coat proteins, that we don't have to go too much in depth on, but we just have to know that it's coated in proteins. But the same exact process happens. The cell membrane engulfs the fluids and takes them inside the cell. It's called pinocytosis. Now we have receptor-mediated endocytosis, which uses receptors to bring in things into the cell. So for example, we have these receptors here, and when they find these whatever connects to the receptor, whatever connects to the receptors, when they do connect to it, and when they connect to it in a bunch, then the cell membrane will engulf the receptors with whatever is connected to it on them and take them inside the cell. And this one, I forgot to draw it, but they also have core proteins. But basically, the receptor-mediated endocytosis means it needs the receptor outside to grab whatever it needs, specifically whatever it needs, and take it inside the cell. and that is receptor mediated receptor mediated endocytosis. Damn it. And that would be it for chapter 7. If you have any questions, just let me know.